Thank you. Good afternoon, everyone. Today I'll be presenting a procedure for estimating liquefaction-induced ground settlement that Professor Bray and myself developed. This is part of a bigger project that investigates liquefaction-induced movements of structures, and the primary sponsors are Caltrans, PEER, the National Science Foundation, and we had also funding from institutions in New Zealand. So I'll just go ahead. And liquefaction-induced movements, after the 2010 Maule earthquake in Chile, there was several bridges that were damaged. For example, the Juan Pablo II bridge. It suffered severe damage after soil liquefaction happened in the embankment in the northeast approach of the bridge. So the embankment liquefied, there was ground settlement, there was lateral spreading that later damaged the structure. And along the bridge, some piers suffered liquefaction-induced settlement. And the mechanisms that are involved with this phenomenon with liquefaction-induced settlement are primarily volumetric and shear-induced settlements. Today, I will be focused on the liquefaction component, the volumetric induced component, so post-liquefaction volumetric induced settlements. And probably most geotechnical engineers know this famous chart by Professors Ishihara and Yoshimine, where you take the factor safety against liquefaction as a proxy for the seismic demand, and the relative density of clean sand as a proxy for the soil state to estimate a value of the volumetric strain. Then that is combined with the thickness of liquefiable layer. You sum them all up to estimate, to get an estimate of the volumetric induced settlement. So, but there is one big caveat here, that this famous chart has been built based on test results on one clean sand, the Fuji River sand, which test results are shown here. And this has been the basis for several methods, as you can see here on the top right. And then we have been applying this chart to many clean sand sites, and also to some silty sand sites, using things like the fines content correction, hoping to convert a silty sand into a clean sand equivalent material and apply this type of procedures. So there is a question if a methodology based on the clean sand can be applied to different other soils. So we went ahead and collected more test results on different materials. So we collected 9 clean sands. So we have 10 clean sands using the Ishihara and Yoshimine original data, 3 silty sands, 5 silts, and 2 gravels. Which are mostly uniform, but they have different particle shapes and were tested at different confining stresses. So we have a wider range of test conditions and materials. And we end up having almost 600 volumetric strain data points and almost 300 maximum shear strain data points. So using this database that you can see here represented by their grain distributions, we were able to revise and produce new models for estimated volumetric and shear strain potential of liquefied soil. Some trends that we observe in our data, volumetric strain trends in terms of relative density. So the first observation is that the volumetric strain and the maximum shear strain during cyclic loading, they have a strong relationship. At smaller strains, as you can see here, as you approach initial liquefaction, and beyond initial liquefaction, there is still a linear trend. So we analyzed clean sands initially. The Ishihara original data is shown in lighter colors, and the new data is shown with darker markers. And as you can see, they are consistent. When we move to silty sands, again, the clean sand information is shown in lighter colors, and the black markers are the new information we collected. Again, we see that they are consistent in the responses, except for these gray triangles. And why is that difference? It's because these materials are silty sands that are well graded, so they have a coefficient of uniformity of 18. And they have a compressible and crushable fine matrix. That means that it's the fine matrix which controls the recompression of these materials. So our approach does not capture that behavior. We are actually limited to uniformly graded materials that are non-plastic. And if we move to non-plastic silts, again, we see the non-plastic uniform silts respond in a similar way to clean sands. So this is the model we are proposing down here. And this model produces this set of black contours that they are similar to the Ishihara and Yoshimine original family of curves. However, we have some differences at really small and really high relative densities. And we see that our new updated model has less spread than the Ishihara and Yoshimine original curves. And again, this new model is recommended for clean sands, non-plastic silts, and non-plastic silty sands. We also developed a different model based on the state parameter as defined by Bing and Jeffries 1985, this equation here. The model is presented down here. And the functional form was similar to the relative density model. And we actually used the relative density information to constrain this model because we only had about a fifth of the amount of data we had available for relative density. So that's an important remark. You can see as the state parameter gets more positive, more volumetric strain is developed, and that's something that we expected to see. But we also wanted to look at the shear strain potential of soil that liquefies, because this is an important parameter for lateral spreading problems, and because it's an input for our previous models. So we generated data for clean sands, silty sands, and non-plastic silts. And that's shown in red here and in gray over here. And again, the new data is consistent with the Ishihara and Yoshimine original data points. However, we did see some differences. For example, here and then here, there are some trends that need to be updated, and that's what we did with our model. We didn't have enough data to work with the state parameter, so we didn't feel comfortable working with that parameter. Okay, so that's the initial information. And now onto the ground settlement procedure. So the lab-based models I just talked about, they come from element test responses measured in the lab. So they may not capture the actual response of a soil column with interaction between layers. So to bring in that information, we collected case histories where liquefaction happened and the soil reconsolidated. We divided our case histories into natural soil deposits and hydraulic fills. Hydraulic fills are man-made, hydraulically placed, whereas natural soils are made by geology. So they are different in nature, and we expect them to respond differently. We have 163 natural soil deposits, 42 hydraulic fills, so a total of 205 field case histories with their summary information here. One important thing here is that to be able to develop a case history, we need pre and post earthquake ground elevation information because we need to calculate what was the settlement after the earthquake. And that's where the Christchurch earthquake the series of earthquakes provided a lot of information for us. About 3/4 of our database comes from the Christchurch event. So that's something again to have in mind. So how do we define a site? This is the Wellington port after the 2016 Kaikoura earthquake. The site was shaken and settlement was observed in several areas of the port. Here you can see an enlarged view of the port on the top left image, where site 4 is highlighted around the other sites. The enlarged view of site 4 is down here, where we have 6 CPTs. And these 6 CPTs, they have similar tip resistances, values of I sub Cs, or proxy for compressibility. They have similar factors of safety against liquefaction triggering, and they have similar LSM severity numbers. So for us, a CPT does not define a site. Instead, a site is defined by an area of similar geology and similar seismic response with a number of CPTs inside that area. Work by Professor Chubinovsky and Dr. Dakal of the University of Canterbury. They produced a lot of information for this port. So they provided us with the settlement information after the earthquake. So it's a combination of the CPTs, the settlement information, and also the geology and the seismic response that constitutes that site for us. So now with the case histories and the lab-based models, we can now go ahead and propose a model for induced settlement. So we have the initial form that it's directly the same form as the Ishihara model. We are recommending you to use our relative density or state parameter models to inform this equation. Just to show you how our relationships looks like, this is our relative density model in terms of volumetric strain versus the factor safety against liquefaction for non-plastic soils. It's similar to the Ishihara one, but has some important updates. And you need an estimate of the factor safety against liquefaction. We're trying to be mean-centered with this model, so we are recommending to use factor of safety against liquefaction that are consistent with a probability of liquefaction of 50%. We use the triggering procedures of Olaya and Idris and Robertson 2009, and we are taking the average of these two. But we realized when we were developing the model that we needed a robust correlation to estimate relative density. We didn't have one. So we went ahead and took advantage of the work of Markham 2015 and Besai 2017. And they produced a lot of information about CLT soils. We had access to relative density measurements, contive resistances, the I sub C parameters for a number of locations, among other important information. So these locations or these points are well constrained, and we have high confidence on the values that we are analyzing. So we were able to propose a relationship between relative density and the cone parameters, as you can see the equation here on the right. Our model is this blue line that follows the data, but we didn't want to use just one relationship. So we also used the Robertson and Cabal 2015 CPT relationship, but we extended it to more compressible materials because it's originally developed for clean sands, so this area. So we had to use their liquefaction correction factor for compressibility to be able to use it. We're using the average of those two. So then we didn't expect our lab-based model to actually capture all the case histories 100% of the time. So we analyze the residuals and we see different trends in the data. But two important ones are the trend that we observe for hydraulic fields and natural fields in terms of the soil compressibility represented by I sub C. So we are proposing to include a soil behavior factor that the effect is that this factor reduces the amount of settlement as the site is more compressible, indicated by higher I sub C values. We're using I sub C 15, which is the average over the first 15 meters in the soil profile. And we also saw an effect of the magnitude of the earthquake. Our interpretation of this effect that you can see here, trends in the data, is that the additional cycles of earthquake loading after initial liquefaction produce more settlement. And that's something that wasn't captured before. So we are including this magnitude factor in that form. So our final model, it's this equation up here. It's the original model that integrates layers in the soil profile, but has the two-factor corrections. And again, there was another factor that was required, this letter C here. And this parameter is just, it captures all other components or all other things that our model does not consider. Right? So it has a value of 1.5 for natural soils. It was set to 1 for hydraulic fields. It was calibrated that way because we think that hydraulic fields are more similar to our lab experiments. And importantly, I want you to know that the standard deviations are in the order of 0.5 for hydraulic fields and around 0.6 for natural soils for both relative density and state parameters. And that's something that we were expecting. We expect a hydraulic field to have less variability compared to a natural soil formed by geology. Some of the model residuals after all the calibration are shown here below, so you can see the model performance. And that should be all for me. Thank you.